welcome to Ask Melissa Maribel Live, where you tweet your questions ahead of time for a chance to get them answered on my next live. Hey guys, welcome. If you are here, let it be known. Say hello in the chat. So far, I see Callie, Madi, Kay, and Brenda. And I see other people coming together. Awesome. Rayhan and everyone. Okay, awesome. So I do see a lot of different questions. If you are new to these live sessions, what I wanted to let you know is I do already have my questions picked for the session. So ahead of time, the week prior, I actually pick all the questions that I got from students who tweeted me. So if you want to get your questions answered for the next live, make sure to tweet me throughout the week. And the information is on the screen. You can tweet me at HelloMelissaM and use the hashtag AskMelissaMaribel so I can see it. And then of course, I decide Friday night, or really on Friday, what questions I'm going to pick and create a whole lesson plan over it. All right, so that's what I'm going to be going over today. I'm going to be going over Faraday's law, finding molar mass of an acid, and net ionic equations. If you guys still have more questions, which I do see a lot of different topics that you guys are requesting right now, and if you need that immediate help, what I highly recommend you do is in the resources of, actually in the description box of this video and all my videos, I have several different resources for you guys. So whether it be online tutoring, if you want to find an online tutor, or if you need specific homework help. So like homework help is more of like solution based. So it shows you, it's called Chegg Study. It shows you a step-by-step solution to that question that you may have. They have a bunch of different questions already in their like solutions bank, or you can literally just ask your question and a tutor will answer it. So all that information and the link is in the description box of this video. So if you do want to check that out, make sure you do so. I personally use it throughout college and it was really helpful. So make sure to check that out. And I did want a little disclaimer, little thing I want you to let you know is I am a part of their affiliate program. That just means I do get a small commission, and all that goes back to making more videos for you guys. Something else. So I finally created my own Patreon page. It's been a while, and I've had a lot of students tell me I should. So yeah, I created my own Patreon page. So if you would like to support my channel, support me in making more videos for you guys and making more notes, making more everything that I do and all the things that I'm working on, you can check out my Patreon page, which I'll link up. I'll put in the chat right now, as well as if you would want to have one-on-one tutoring with me, then you can. So I open up a few spots on Patreon if you would like to have one-on-one tutoring with myself, or if you would like a small group. So kind of like what we're doing here in a sense, but a smaller group, and you do get, your questions answered. So there's also that option as well, group tutoring or one-on-one tutoring. You can check that out on my Patreon. All right, so let's get started with the first topic, which is Faraday's law. Okay, so with Faraday's law, the main thing is that there's so many units to this. And I think that's where students get kind of thrown off by it. It's by the units. When do I use it this way? Or also, what do I do with all the formulas that I have and when do I use that? So we're going to go over 3 different examples to understand when to use the formulas, when to use what units, and so on. And the 3 different main questions that I typically see with Faraday's law is you either are asked to find mass or time or current, which is measured in amps, but we'll go over all that. So first things first, what's our formula? So the formula that we're going to typically see here is going to be these 2. All right, so it could be either or we could actually set both of these equal to each other since Q and Q equal each other, right? So we can set both of these equal, and that's something else that we will see. We will be doing this a lot for all these different questions. So let's just go over what this all means, what every single variable or symbol means. So Q refers to the charge. So our charge is measured in C, which is not Celsius, it's coulombs. All right, so it's just a measurement of charge. And then next we'll see N. N is just moles. I is going to refer to our current, which is measured in amps, which is referred to as A. All right, and the next time, or T, is going to be measured in seconds. So all of these, make sure that you always have all of these correct units before you start plugging everything into your formula, or else it won't be correct. So make sure to have your Q or charge in coulombs, N in moles, I is current in amps, and then time in seconds. And then next, this is some more things that we're going to see. All right, we're going to see some units here. So the next thing that we're going to talk about is Faraday's constant. And you're going to see different variations to this, but really it's the same thing. All we're doing is we're changing up our units. So like these two are the exact same number, but instead of coulombs per mole, here we have joules per volts per mole. So in this case, it's just a tiny bit different. It's dependent on whatever the question is asking you to solve for. So sometimes they're going to be specific and say, oh, I want my answer in volts. Oh, I want my answer in coulombs, or so on. And then that's how you know which Faraday's constant to use. And then something else to note for your units is that 1 volt is equal to joules divided by coulombs. And then 1 amp is equal to coulombs divided by seconds. This one is definitely one to know, right? I see this so much. And we're going to see this throughout the 3 different examples as well. And then the other thing here, this one, beware. So this one tends to confuse students because we're dealing with electrons. And sometimes it feels like, when do I divide by electrons? When do I multiply by electrons, and when do I not? So it's going to be dependent on the question asking or talking about different ions. So it's going to show like a change in oxidation numbers essentially, which we'll go over. So, okay. And then this is just another one that we'll see. This is going to be our Faraday's constant when we're using electrons. And then this one's rounded. You could use either or. It could be 9.648 times 10 to the fourth, or it could just be rounded, and we'll round that up to 5. Either one is correct. Okay. Now that we know what everything means, which Faraday's constant we use, let's go over our first example. So this question is saying someone wants to plate a teapot with 10 grams of silver. If the process takes 84 minutes, what average current has been used? All right, so as always, if we don't know where to start, let's just start with identifying what we're given and what we're finding, and then that'll help us figure out what formula to use. So essentially what we're given is just our mass, so we're given our grams of silver, and we're given our time, which is in minutes. But remember, our time, we always want time to be in seconds. And then also for grams, we don't want anything in grams, we want something in moles, which we'll go over. And then what we're asked to find is our current. So our current is going to be it's going to be found in amps. So A is amps, that's what we want our unit to be. Our formula is going to be these two formulas set equal to each other or combined. So this is going to be our formula. And the reason why I can do that is because we're not given our charge. So since we're not given our charge, and another thing, if you don't know if they literally don't say this is your charge, then you can identify it by just looking at the units. So since nothing is in coulombs, I know that, no charge is given. So instead, and we can see that by the units as well, that grams has to be mass and minutes has to be time. So that's how I know to use this formula, because I don't know what Q is. But I do know there's a way for me to figure out the moles, which is N. I do have Faraday's constant, and then I is what I'm solving for. That's the current. And then I do have time, which is going to be measured in seconds, so we do have to convert this. So that's something right off the bat to notice. We have to figure out, or we have to change all the units that are initially given to us. So I know I have to convert these grams to moles and convert the minutes to seconds. And that's exactly what I'm going to start off with. Oh, and this is the coulombs, this is a Faraday's constant that I will be using in coulombs. All right, so let's start. First things first, we'll find the moles. So we have 10 grams of silver. I'm going to divide this by the molar mass found on the periodic table of silver. And then from there, our grams and grams cancel to give us our moles of silver. So far so good. Next thing I want to do is just change the minutes to seconds. So I started off with 84 minutes, and we'll think how many seconds are in a minute. So in 1 minute, there are 60 seconds. Multiply that, and that's how many seconds we have. Now we can plug everything into our formula. So now we're going to solve for I, which is our current. So plugging everything in, we found our moles. We have Faraday's constant. That will be given to you. And then next, we are looking for our current. We just converted everything to seconds. Since everything is in its proper unit, I can then just cancel things out. So those two would cancel. And the next thing I would do is actually divide both sides by the seconds to give us our results. So here, that cancels. This gives us current, which is, so far, it's going to be in coulombs per second. And we can see that with the units because our moles canceled, but we have coulombs here and we have seconds on the bottom. All right, so that's not it just yet. All right, so we're almost done. We have the correct answer. It's just our units that need to be changed. So remember that 1 amp is equal to 1 coulombs per second. So I could easily just say, okay, since it's a one-to-one relationship, it means it's literally the same thing. I just have to change the units. So 1.8 amps will be our answer for our current. Okay, let's try another one. So, and what I'm doing right now, I'm talking about Faraday's law, Faraday's constant, how to use everything, and the formulas, and the 3 different types of questions that I've seen on exams, homework assignments, extra credit assignments, so many different things. So these are just 3 common examples to help you out. So for this next example, let's see what we're finding. So we have, for corrosion resistance, a steel bolt is plated with nickel from a solution of nickel to sulfate. If 4.25 grams of nickel produces a plating of the required thickness, how long in hours will this process take if a 720 milliamp current is used? All right, so a lot of things going on. But first things first, let's just figure out what we're given, what we're finding, what formula we're using. Okay. So initially, we are given our grams of nickel, which is the 4.25, and we are given our current, right? Because one, it does tell us, right? That tells us if a 720 milliamp current is used. So I know that this is my I. But something that you'll note there is that the unit isn't correct. We don't want milliamps, we just want amps. So I will convert that in a second. And then also, I'm not going to want grams because that's not part of my formula. Moles is part of my formula. So once again, we will convert the grams to moles. And in this case, we are finding time, which will be measured in hours. So once again, we'll be using the same formula. You will see this formula commonly used. If they were to have given you the actual charge, then I would have used the Q equals N times F or I times T, dependent on what you're given. Okay. So in this case, let's just keep going. And then since I know I'm finding my time, what I have to do now is looking at the units. N must be in moles, so I have to convert the grams to moles. Faraday's constant is fine. Our current is not okay, so it needs to be converted to amps, and then we're actually going to have to convert it to coulombs per second. And then we're also going to find time, so that's going to be the whole purpose of this. Okay, so let's start off. So here we have our coulombs per mole, and then what I'm going to do is I'm going to find my moles overall. So all I have to do is divide by the molar mass of nickel, which is found on the periodic table. So in this case, this would give us this amount of moles. Next thing, I want to convert to amps, so going from the milliamps to amps. So all I have to do is divide by 1,000 milliamps, because there's 1,000 milliamps to every 1 amp. And then I get 0.72 amps. But I want to convert this. So I don't want to be using amps in this case. I want to convert it to coulombs per second. The reason why I want to do that is if we didn't, actually first, Faraday's constant is measured in coulombs, so I do need to have that to cancel out the coulombs. Another thing is if I didn't convert it to coulombs per second, then I wouldn't have any unit of time, which is what I'm looking for. So that's kind of where our unit of time comes in when I change that. Next thing is just to plug everything into the formula and solve for time. Okay, so I plugged in the moles that I found. I plug in Faraday's constant. Why do I want to say coulomb? So Faraday's constant, and then next I'm just plugging in the current that I converted to coulombs per second. Next thing's next. All right, so I'm going to divide everything over now, just to get time by itself, and then we'll see what cancels out. So what's going to cancel is our moles and our moles, our coulombs and our coulombs, but seconds is going to be left on top. So that's why I wanted to convert this to coulombs per second, because time has to be measured in some sort of unit of time, right? So in that case, what I'm going to get is this amount of seconds, but our answer wanted it in hours. So we're first going to convert this so we're going to go from seconds to minutes, then from minutes to hours. So we know there's 60 seconds per every 1 minute, and there's 60 minutes per every hour. And then all I have to do, hold on. I know it's a little bit messy here, but I would multiply these two first. So we get this. And then I would divide these two values. So this divided by that 3,600. And then I would get 2.7 hours, and that would be my answer for that one. We'll do one more for Faraday's constant or Faraday's law, and then we'll move on to finding molar mass of an acid, and at the end we'll talk about net ionic equations. Okay, so next one. Next one says a car bumper is plated with chromium using chromium-3 ions in solution. So I'm going to stop right there. That's a hint right there. All right. The fact that they're talking about ions in a solution, that most likely means I'm going to be using the Faraday's constant that has electrons, just because they're literally saying it's going from chromium. So chromium in its solid state. So chromium in its solid state would look like this. And it's saying it's going to chromium-3. So remember this Roman numeral just refers to the charge of your metal or your transition metal. So this would have been a 3+ charge. And of course, this is aqueous. So this goes back to a little bit of oxidation. So oxidation numbers, in this case, this would have been an oxidation number of 0. Remember, anything that is one element in its solid state is going to have an oxidation number of 0. And then anything that actually has a charge already is going to be the oxidation number itself. So it would be +3, or it would be 3. I'm not going to use the actual charge. So it would have been 3. So the fact that what that actually tells me is there's going to be 3 different electrons. All right. So that's essentially the concept here. So this is going to be oxidized, meaning it's here. So it's becoming more positive, right? Because we have that 3 going up. And in this case, this would have been oxidation, or really, I just want you to think that 3 electrons are moving. All right. So that's going to help us in the future. So let's continue with this question, and then I'll continue back to the 3 electrons. So the next, what this is saying is if a current of 54.2 amps flows in the cell for 45.5 minutes, predict the mass of chromium deposited on the bumper. Okay, so we know there's 3 electrons. We know our current, right? That's our amps. So I'm going to say that this is I. This is our current. And we also have our time. But our time is not in the correct unit. We're going to have to convert that to seconds. And then what are we solving for? So we're solving for the mass or grams of chromium. Okay, so we have our same formula that we will be using all throughout. I don't think I put it here on accident. Here, I'll rewrite it here. So our formula that we're going to be using is what we've seen before. We know this because we're not given a charge, right? So this is N times our Faraday's constant is equal to our current times our time. So I'm still using this formula. All right. So in this case, what I'm going to do first is just convert the minutes to seconds. So starting off, we know that there's 60 seconds in a minute. So multiply those two together, and that's how many seconds I have so far. Next, I'm going to find the moles. So I would plug everything into the formula that I initially had. And remember, that formula was just N times Faraday's constant is equal to our current times our time. So something to note, by the way, what I did initially already was this was in amps initially when we were given our current. I just converted that to coulombs per second. And the reason why I did that is because Faraday's constant has coulombs, and I need some sort of coulombs to cancel out. Plus, I also need those seconds to cancel out. So when you're plugging it back into the formula, your current should be in coulombs per second. When you're solving for current, you will then convert it to amps. And then from here, what I'm going to do is, the seconds cancel. And then next, all I would have to do is divide this entirely over, but you would think that, but you're not done. The fact that we're using the electrons in this case is because we went from the chromium in its solid state to chromium ions, which has a 3+ charge. So what I have to do is I actually have to include those electrons. And where I'm including those electrons is right here. The reason why I'm doing that is so electrons and electrons can then cancel, and I can just get the moles that I wanted. So I do have to multiply by Faraday's constant by the overall electrons that are being moved or either being gained or reduced or whatnot, or lost. So that's why I used 3 electrons, because when we were talking back about the chromium solid going to chromium 3+. So in this case, our electrons would cancel. Now our seconds would also cancel. And then now I can continue doing the math. So I would have gotten, after I did the math here, I would have gotten this amount of moles. Last up, since this question did request it in grams, I'll convert this back down to grams by using the mass of chromium. So I would multiply this by the molar mass of chromium, and our final answer for chromium would be this. All right, so this was 3 different ways that they can ask a Faraday's constant or Faraday's law examples. One, finding, I think the first one was finding current. The second one was finding time, and the third one, finding the mass. So make sure to study up on those. Knowing those will be extremely beneficial for anybody who is taking the second half of chemistry, or if you're in AP Chem and you're covering that now. So awesome. Let's continue on. All right. So this next question is going to be finding the molar mass of an acid, and we will be using molarity or concentration as our conversion factor. So this is going back to stoichiometry. So for everyone who's struggling a little bit with stoichiometry or with molarity, then I highly recommend you take notes or just make sure you know how to do a question like this. All right. So let's look at this first question. So a 0.659 gram sample of an unknown monoprotic acid. So since we don't know what it is, this is just a generic sort of setup saying that this is H and A. A is just going to represent some sort of halogen, or an HA is just some sort of acid. So it's not specific, which is okay. And then next it's saying is titrated with a 0.1 molar solution of potassium hydroxide if the volume of the base needed is 33.15 milliliters. What is the molecular weight of the acid? Okay. So in this case, what I want to do first, because I'm finding the molecular weight or molar mass, what I want you to think of is, what are my units there? That's going to be extremely beneficial to help you understand what you already have in the question and what you're missing and you need to find. So for molecular weight, the unit is going to be grams per mole. Now we're finding the grams per mole, or really the molecular weight of the acid. So we already are given the grams of that acid. So this first part is done. What we need now is the actual amount of moles. So that's what our whole entire stoichiometry thing is going to be here, or setup of this question, is just to figure out the amount of moles, and then we'll divide the given grams divided by the moles that we found, and that's your answer. So let's do that now. But I want you to know that we're given, and let me see if I put that, before I move on. They didn't give you a balanced equation. So assume that you do have to create one. And this one isn't so bad because remember, this is going back to our acid-base neutralization reactions. And that's what titrations are. They're acid-base neutralization reactions. And all that means is that we combine an acid plus a base, and that gives us a salt and water, H2O. Okay, so our acid here is going to be that generic one, which is just HA. I know it's an acid because it starts with an H. I know it's a base because it ends in OH. So in this case, what's going to happen is, remember, this is going back to the inner and the inner, outer and the outer. And all that was my little trick of predicting products with double displacement reactions or double replacement reactions. So this is where these inner elements combine. And we always want the metal first, which is positively charged, and then the nonmetal, which in this case is going to be represented as A. So A is going to be, let's say it's -1, and then K would have been a +1. I know that A would have been -1 just because there is no subscript on H. That's how I knew. Okay. And then what would happen here is this would literally just be Ka. All right, I know it's a little bit strange, but that's how you would look at it. And then now this last part is just water because H and OH combined would give us water. Okay, so the steps for this, and I think that's what I have next. Yeah, so first things first, find the moles of our acid. Second step, divide the given grams by the moles of our acid that we just found. So let's do all this. So what I want to start off with is I'm going to start off with the milliliters of our base or potassium hydroxide that's initially given. And let's just go over our plan, all right? So I'm going to go from milliliters of potassium hydroxide to the liters, since I do want to convert that. And then next, using the molarity that's provided, so we have our molarity here, the molarity of potassium hydroxide, I will then convert that to moles. And then lastly, using the balance equation, which it is balanced, I don't have to do anything else. Everything does have a 1 coefficient. Then I know that, okay, then I can just convert that to moles of our acid and I'm done. So that's what the setup's going to be. This is what the plan's going to look like. So let's start this off. Starting off with our milliliters of potassium hydroxide, I'm just going to convert that. We know 1,000 milliliters is equal to 1 liter. So I would do that first. Our milliliters and milliliters would then cancel. I'm now at this step. And something to note, when we're talking about molarity, recall that molarity can really be broken down to moles divided by liters. And what I want you to know or think of for this is actually telling me 0.1 moles of KOH is on top per every 1 liter. That's how we would break that down. So whatever value is initially given here next to molarity, that's going to go on top with the moles, and it's going to be per every 1 liter. Yes, always. It will be like that. All right. So that's how we would look at it. So now this is going to be used as our conversion factor in this case. This is going to be our next step. That's how we're going to get to moles of KOH. So that's how I know, okay, I place the 1 liters on the bottom because we always want those units to cancel. And then from here, the liters and liters will cancel. And so we're on this step now. We're at moles of KOH. Next thing is remember that all of these have a 1 coefficient since everything is balanced. So all I have to do now is do a mole to mole ratio that comes from my balanced equation. And then I'll align the units. So of course they can cancel. So 1 mole of KOH and I found that here. And then per every 1 mole of HA, which is just our acid. And once again, I found that here. So what I would do first is multiply the top and then divide by 1,000. And then that would give me the amount of moles of my acid, but we're not done yet. So next we want to actually divide the given grams that we were initially given by the moles that we just found. So initially we were given in the question the amount of grams of that acid, right? So that's what I'm going to have here. That's what I'm taking away from this question. Then I'm going to divide by the moles that was provided, and I just found the weight. So then that would give me 199 grams, and we're done. That would be our molecular weight of the acid. So that's something that I definitely know. Actually, what helps me a lot, what helped me a lot, what helps a lot of students, is just seeing what the units are for the what you're finding, right? So if like this were asking for the density, then I would know, oh, density is mass divided by volume. So I would know, oh, it most likely is going to be grams divided by liters. So I need one of those, right? But if it's molecular weight, I know grams divided by moles. What am I missing here? I'm missing the moles. That's what I have to find first, then divide at the end. So that's going to be really beneficial. If you guys need more help with molarity, I do have a video covering it. It does help you use molarity as a conversion factor. I believe I was finding mass. Don't remember the exact question per se, but I do remember it was a really good question for using molarity as a conversion factor. So I do go over every single step there. So make sure to check that out. I'm going to put the link in the chat right now. And then there's also a practice problem in the description of that video as well if you need additional help. And at the bottom of the description box, you'll find the step-by-step solution for it. So make sure to check that out if you're struggling with molarity. So, all right, let's keep going. And let's see. Okay. So now this other topic, I know a lot of you guys are wanting this topic of net ionic equations. And what I want us to go over and think about first with net ionic equations, this is going to be really beneficial if you know how to use a solubility table. And understanding what a solubility table does or is and why we need it, it's pretty much just helping us distinguish, is something going to dissolve in water, all right? When we're talking about solubility, that's what we're talking about. If something is soluble, that means it dissolves. If something is insoluble, that means it doesn't dissolve. So And something else to note is that our different phases, if something is aqueous, that means it's soluble, meaning it dissolves. So aqueous, soluble, dissolves. If it is a solid, it's insoluble, meaning it does not dissolve. All right. So solid, insoluble, doesn't dissolve. That's going to be extremely beneficial to understand. And I just I made a solubility table for you guys. So if you want to download that, it's a lot easier to use. So if you want to download that, it is free. It's in the chat right now. And I also have a video going along with how to use the solubility table and explaining it, and even going over several different examples at the end to help you understand what to do. All right. So this question is saying to write the net ionic equation for this, but it doesn't give you the products. All right. So they just give you your reactants, which is an acid. And we can tell that because it starts with an H, right? This is actually acetic acid, where this is acetate. So how I know this is acetate is just by memory. So remember, you do have to memorize your polyatomic ions. That is something to definitely know. So I just know this by memory, that it doesn't have this H here. It's just from the carbon to the oxygen, that's acetate. And then with our H in front, that's acetic acid. That goes back to naming acids. So I have an acid, I have a base. I know this is a base because it ends with an OH. So what I'm going to do is I'm going to figure out how I'm going to combine and predict the products. So remember, this once again goes back to the whole trick of the inner elements go together to form our first reactant, and the outer elements go together to form our second product. So to form our first product and our second product. So that's what I'm going to do. First things first, I'm going to combine our inner elements together. Remember that we always want to be positive before we're negative, meaning we want the positively charged metal to go first. So metal goes first, then the nonmetals, or in this case, our polyatomic ion, which is negatively charged. So Na has a +1 charge. What's next is going to be our acetate. And then we see, everything is balanced. Our charges are totally fine. We have a +1, a -1. Those cancel to then give us our first product of sodium acetate. And then next, I really stated that it is aqueous, but something to just double check and to help you understand how we can figure that out is this is my solubility table, by the way. So how we're going to use the solubility table is I like to look at, and in this case, it doesn't necessarily matter, but I typically look at the end. All right. So I would look at just the acetate. So I'm going to look at this end. I would just look at the acetate and I'd see, where is acetate on this table? Well, it's right here. And does it have any exceptions to the rule? No. And how we use this table is this is essentially this little portion up here is saying all of these are going to be soluble, meaning they're all aqueous, with the exception of anything here. Like if we had a halogen like chlorine and that had, let's say, lead in front of it, then I would know that it would be a solid, it would be insoluble. But in this case, there are no exceptions to this rule, so acetate will always be soluble. So I know, yep, that's totally fine. It is going to be aqueous. And then next, this next one can be a little bit tricky, but just know that what we're solving for, what we're figuring out, this is going to be water because we have H plus and OH minus that will form water. But how would you have known it's a liquid? So just know that when we are doing, once again, this is going back to an acid-base neutralization reaction, where we have an acid and a base, which forms a salt and water. And your water will be a liquid. So that's pretty much the main thing to have known here, is that your water isn't going to be aqueous, it's going to just be the liquid, right? So that's what I kind of want you to think of. Like when we're talking about something being aqueous, that means, or even soluble, it means that thing is going to actually dissolve in the water. So why would we have water dissolving in water? You know what I mean? So that's kind of like what we're talking about there. We're just going to have water as the liquid itself. So that's how I knew that water had to have just been the liquid. All right. So great. This is actually going to give us an ionic equation. If everything were aqueous, then there would be no reaction for our net ionic equation. Why? Because everything would then separate, and since everything would then separate, everything would then cancel, and then that wouldn't work out. So beware of those types of questions if everything were aqueous, that would mean that there's no reaction for our net ionic equation. But let's keep going with this question. So next thing we want to do is, since we have our balanced equation and everything is balanced, what I'm going to do now is figure out the complete ionic equation. It's also referred to as our total ionic equation. And with this, you always want to separate out. So what we're going to do is we're going to break all of like the acid, everything that has aqueous. All right. So everything that has a phase of being aqueous, we're going to break that apart into its separate ions. And we only do that with aqueous. That's it. All right. So we're not going to see that with a solid. We're not going to see that with a liquid. So in this case, I'm just going to break that apart for aqueous only. So that's what I'll do here. So remember that in this case, what are the two different ions that are combining together to form that acid? Well, I know this is H+, and then this is acetate with a negative charge. And then remember that what you do have to do is this still has to state the state of it, so it is going to be aqueous. And then in this case, this is what I would have. Okay, I'm going to do the same exact thing for NaOH, where Na is going to be a plus charge, and then OH would have been a negative charge. And then from here, I'm going to keep going. So I'm going to break apart the product. So Na would be on its own, and then our acetate would also be on its own. But I'm not going to separate that water because it's not aqueous. So this is going to stay intact. Next, we're going to cancel out something known as spectator ions. So what spectator ions are is they're essentially just ions, or remember an ion is really just like a charged element or charged compound, where it's going to cancel out, meaning your spectator ions are ones that we share on either side. So in this case, what do we have in common on our reactants and our product side? Well, we have our acetate. So that would cancel out. Those are our spectator ions. Another spectator ion would have been our sodium ion. So sodium would also cancel out. And then here, what you're going to see for your net ionic equation is whatever is producing that liquid or solid or whatever thing you're looking for that isn't aqueous, we must have had the reactants to actually form that, to give us that product. So that's a great way to check if you did everything right, to see, do I have the ions or the reactants to actually build and make this product of, in this case, water? So yes, we do. We do have H+, OH- does form our water. So I know my net ionic equation is then just that. So that would be it for my net ionic equation. So I hope that makes more sense for net ionic equations. I do have a video going over another type of net ionic equation. That video is great because I go over everything from the very beginning. I do balance it. I do show how to predict the products again. It is a little bit of a trickier question, so make sure to check that out. I do see that being on a test question. I know finals are coming up, so that is a possible test question for sure. So I just put that in the live chat. So make sure to check that out if you guys want more help with net ionic equations. I do have that video. And then let's see how everyone's doing. Okay, so I do see a lot of people asking a lot of questions. I just want to see how we're keeping up with everything. You guys have a test coming up. Wow. All right. And just out of curiosity, when do you guys have your finals? Just to know how you guys are doing. Let me know in the chat when your final is, guys, because I would love to know when your finals, I know they're coming up real quick. I know a lot of people have finals in like the second week of December. I know that's pretty common, but let me know. And then let's see. Any other questions? I don't have any videos on half-life as of now. I do have one. Oh, yeah, I did have one on integrated rate loss, but not on half-life. Yeah, I haven't done that video just yet. Sorry, guys. Okay, so let me know when your guys' finals are, if you know when your finals are this week and next week. Wow, okay, that was quick. January. Wow, you guys have some time. Last exam tomorrow before finals next week. Next week is your finals. Okay. You in January. A lot of you guys are in January. Interesting. So you have more time with that. Okay. So I did have Jessica just asked exothermic reaction. I think that was part of something else. How to find the change in enthalpy in an exothermic reaction. I believe I have some videos on that. I just released an enthalpy video. Let me see if I can find that for you, Jessica. But if not, I know I have Hess's Law, which does cover a little bit of that as well. Let me see if I can find it. If I put enthalpy, yeah. Let me see. Let me see what I have of that. I know I have enthalpy stoichiometry. I see. I don't have... I'll put everything that I do have, Jessica, just so you have it. So I do have enthalpy stoichiometry, which I'll put in the chat, and that's finding heat and mass. And yes, some of them I believe it's heat released. Yeah, so a couple questions are about exothermic reactions, which is just heat released. So I'll put that in the chat. And I also have another topic on standard enthalpy of formations, which I'm sure you'll have to have some of that. So I can put the standard enthalpy of formation one, where I also talked about heating curves and buffers in there, but I'll put that one as well in the chat. Okay, so that being said, guys, next Sunday, next live is actually going to be the last live of this semester. So what I highly recommend you guys do if you have questions, which I know you guys do, make sure to tweet me ahead of time. So if you tweet me sadly on the day of, I already made the lesson, so these lessons don't just take 5 minutes, they take several hours to make. So make sure to tweet me ahead of time all of your guys' questions. Next Sunday will be the last live that I will be doing. So let me know ahead of time. The earlier, the better. So throughout the week, I'd say from Monday to Friday, tweet me at Hello Melissa M. Use the hashtag AskMelissaMaribel, and I will answer as many questions as I possibly can for my next live. So pretty much everyone and if you don't have a Twitter, make one, guys. It's literally free. This is, free tutoring that I'm doing here. So make sure to tweet me any of your questions that you guys have. I will be taking one question from each person just to be fair and to help other people out, of course. So make sure to do that. And Amber says, we know you work hard to help us all. Thank you. I'm glad. I appreciate your appreciation. Thank you, Amber. And another thing that I did want to mention is if you guys still need more help, if you would like one-on-one tutoring with myself, or if you would want, it's kind of like more of a group sort of setting. It's like a Q&A, but it's a smaller setting. I also have that on my Patreon page, which I finally made. So I can put the Patreon link again right now. But if you really want more help before your finals and you enjoy my teaching, then definitely check out my Patreon page. There you could choose to either support me just with a few dollars that go to making videos and any different costs for making videos, or if you would like just help in general with tutoring that I can assist you with, then sign up there. Another thing is something else that I did want to mention is there's even more resources in the description box of this video. If you guys need more help with, like, let's say homework help, I used this in college. It was something called Chegg Study. It was really helpful. A lot of times I had no idea what I was doing on my homework, and sometimes there's that one question that you've tried so many different things and sadly it's still not right, so you're just like missing one little step. So it was really beneficial to see that Chegg Study had all the steps like written out, so it was a step-by-step solution thing. So and if they didn't have my question, then I can literally ask it and a tutor would answer it. So that was really helpful. So make sure to check that out. That is in the description box of this video. So that's another resource for you guys, in addition to the Patreon page that I personally would assist you on. Okay. And Jessica actually just said, I just bought your thermochemistry guide. Amazing. Thank you. Thank you. I appreciate that. I'm glad you guys really like the notes. And that's something else. If you don't know, guys, I do make my own digital notes. It is like it's a guide, essentially. Like Jessica just bought a thermochemistry guide. That one was over 50 pages of information, of examples, of everything I can possibly think of that you will need to pass your test on that. That's exactly what I make my guides for, because I know what it's like to be studying late at night, reading your book over and over and just not getting a word of what it's saying. So I wanted to make those guides to avoid that frustration and super late night studying. So yeah, awesome, guys. All right. So I hope to see you next Sunday. Tweet me throughout the week and have a lovely Sunday, guys. Good luck on all of your exams, and I'll see you next week. See you guys.